All right, we've already covered part of this chapter. We talked about Ohm's law, resistors, and did a lab where you measured, set the voltage, you measured the current, and saw that the relationship between voltage and current obeys Ohm's law with resistance. Now we want to talk about putting resistors in series and parallel, similar to what we did for capacitors. Our basic circuit is a battery and a resistor, no resistance in the wires. We talked about color coding for the resistors. This is called DC for direct current, as opposed to alternating, which is what you usually get out of your wall, which was called AC. We'll talk about that later. DC generally is constant, or it can be time dependent. We'll talk about that later too. There's our model, and the model we're using here for example, a battery would include an internal resistance of the battery and our load resistor. We'll talk more about Kirchhoff's law, but it says that if you walk around the loop, then the sum of the energy gains has to equal the energy losses. Here the battery's a gain, the two resistors are a loss. And so the model for a battery includes an internal resistance. For an ideal battery, that would be 0. For a real battery, when you try to draw, if you just touch your voltmeter across these posts, it'll measure 6 volts or whatever the battery says. But if you put a load on it, there will be a V equals IR loss here due to the current in the resistor. So your load voltage will drop. Like we said, if we've seen this type of connection with capacitors before, two resistors connected in series. They're in series because whatever, thinking of water, if I have my current or water flowing through, whatever goes through the first one has to come out and go through the second one. That's a series connection. It means in this case that their currents will be the same, but their voltages will add. So if I say the voltage across each resistor, which obeys Ohm's law, has to add up to the voltage of the battery, and then I replace V equals IR, knowing it's the same current everywhere, divided out, I get that the equivalent resistance, replacing these two with a single resistor that draws the same current, would show me that the equivalent resistance here is the sum of the two resistors. Parallel connection. Again, we talked about how you have to be careful and not just think of the parallel picture on parallel wires, which is where the name comes from, but more fundamentally, the voltages have to be the same. And what that means is I should start with the battery. I can go through R1 and back to the battery, or I can go through R2 and back to the battery. Parallel is sort of an OR case. The equivalent resistance to those two is going to be found by saying that the currents add. Current out of the battery supplies both currents, adds up here. I is I1 plus I2. Again, Ohm's law equals IR, solve for I. You replace it. Everybody's got the same voltage because they're in parallel, and you get the 1/over law that we've talked about earlier for capacitors. Notice it's swapped for resistors and capacitors. So in summary, and this is how we're going to work some more complex problems, is we'll take a complicated circuit, break it down using the rules. To get the equivalent resistance, then we'll replace two resistors that are in series with a single one that's got the sum of the resistance, parallel with single resistor that has that 1/over law. And then we'll walk back through the pictures, bringing back like we did before. If they're in series, the currents are the same. If they're parallel, the voltages are the same. So here's a simple example. We got a 3 and 6 ohm battery in series with an 18 volt battery. So we can replace then with a single resistance of 9 ohms, and it will draw the same current. You take the 9 ohms, use your 18 volts, and you get 2 amps. And so they have 2 amps of current in both the equivalent and in each of these. I could then use and calculate the voltage in each. Which has the largest current? Well, they have the same current. Which has the largest voltage drop? These are the type questions that you might see on the quiz. If is R equivalent larger or smaller than R1 or R2? Well, they have the same current. V equals IR. Since they've got the same I, the voltage will be the largest of wherever the R is largest. The equivalent resistance, since it's the sum, will be larger than both R1 and R2, so it won't be smaller than either one. Take the same two and connect them in parallel. 3 and 6, 18 volts. They'll both have the same voltage. Their resistance, though, will be the 1 over law. 1 over 3, 1 over 6, common denominator. You get a half, you flip it, and you get 2. So I could replace both of those with the 2. The current out of the battery would be the 18 over the 2, or 9 amps. But then I could then calculate the current in each one using that same 18 volts since they're in parallel. So 18 over the 3 would give me 6 amps. 18 over the 6 would give me 3 amps. Notice the 3 and 6 are going to add up to our 9. Same voltage across both. Which R has the largest current? Well, this is the old current follows the path of least resistance. You notice the larger resistor has the smaller current. The smaller resistor has the larger current. Which R has the largest voltage drop? They have the same. And notice the resistance is smaller than either of them. Okay? Now, the type problem we'll want you to do is, given several resistors, what's the equivalent resistance, and then what's the current? If I tell me the battery is connected to it, what would be the current in each one? So here's a typical. We've got an 8 and 4, and again we do them in pairs. Our 8 and 4 are going to be in series, so we add when we replace it with a 12. Our 6 and 3 are in parallel, so we're going to do the 1 over law. 1 over 6, 1 over 3 gives me 1/2. Flip it over, we get a 2. These two are now in series, and so 14. And so I could either have a 14 or I could have this combination. And if they were both in two black boxes I couldn't see into, and all I could do was measure the current and voltage going into it, I wouldn't be able to tell the difference. DC circuit. If I then apply a 28 volt battery to it, then I could say, well, Ohm's law will tell me the current, and I get 2 amps of current. But I don't have a 14, I've got a 12 and a 2. So they were in series, so I say, well, then the 2 amps of current is not only in the 14, but it's in each of these. So I bring the current to the picture, and I can then calculate the voltage across each. I times R, so 24 volts and 4 volts. Notice that's going to add to our 28. But I don't really have a 12 and I don't really have a 2. I have a series and a parallel combination. So back to the next picture, the 8 and 4 are in series, so they have the same current, the same 2 amps. So I could then calculate their voltages by using the 2 amps. So I get 16 and 8. I don't have a 2 here, but I've got a 6 and a 3. They're in parallel. They have the same 4 volts. So I can use that 4 volts and Ohm's law then to calculate the amount of current that is in each one. 2/3 and 4/3, which will add up to be the 2. And so now I have the voltage and the current on each of those resistors. And that's the sort of thing we're going to ask you to do on the test. That's in doing circuit analysis, the first thing is to be able to do these series and parallel combinations. It's similar to what we did in capacitors, though you have to watch out because your laws for the equivalence are different, though the rules for what's the same and is the same. We've used some meters in class. Typically the older meters were made out of a a galvanometer, which was made out of, and we haven't really talked about this yet, but it's made out of a coil of wire and a magnet. And we'll see that if you put a current in a coil of wire, it'll cause a torque if it's in a magnetic field and cause it to rotate. But these measure small currents, and then we make them into either a voltmeter or an ammeter by putting resistances in series and parallel. Remember, an ammeter measures current. Ammeter must take all of the current to measure it, but we want it to have a very small resistance. Your galvanometer has one, but to make it even smaller, we'll generally put a small resistor parallel with our ammeter, so that we affect it. Have a very small resistance, it won't change things much. So it's called a shunt resistor. Can take the same galvo and make it into a voltmeter. Remember, the voltmeter measures potential difference. It has to go across or in parallel with what we're measuring. Ideally, it doesn't draw any current. A real one does. It's made out of a galvanometer, but we're going to make it have a very high resistance, so all the current will stay down, or most of the current will stay down here. We put a very large one in series, usually mega ohms. Galvanometer is typically 50, 60 ohms, and so we're going to put a mega ohm in parallel with it to keep the current down. In your household, interesting to think about. If you think about it, it's a perfect example of a parallel combination, because you can go into your house and turn on different switches in different rooms, and the lights will come on, which means the other light stays off. That's a parallel type connection, and that's symbolized here. That's our battery, so to speak. You've got a circuit breaker for protection, but then you've got a set of switches. You switch any switch, and you're connected. The way they represent this is with the ground, so you're going to be able to go through the meter, through and to your ground. The reason electricity is dangerous is because, of course, it doesn't work well with our bodies. Our bodies have a low resistance, so if we somehow accidentally connect ourselves in parallel to a high voltage, we got a low resistance. The current's going to want to go through us. Turns out that AC and DC are different. DC is not as dangerous. AC is so dangerous because essentially the electrical signals in our body that make our brains work, make our hearts beat, are similar to AC, and they have frequencies that are near the 60 frequencies that we typically use. So a very small current can cause an electrical shock. AC can cause your heart to stop beating, so you die of a heart attack, essentially. That's the reason, that people do CPR. How you get your heart beating back again. DC, if you were to be, you're going to get, the problem there is ohmic heating, and if you stay in it long enough, you'll basically be cooked, which will be true in AC too if you stay long enough for a large current. 5 milliamps or less can cause a mild shock. 10 milliamps or less will cause your muscles to contract and you can't let go. 100 milliamps will essentially kill you. That's for AC. For DC, you won't hardly feel 100 milliamps. And that's an example of making sure that there is an alternate path beside your body that will get you to ground, that has a lower resistance than you do. Outside, you have to use GFI, ground fault interrupt, and that again is to make sure that you have an alternate path other than you, so there's current to flow, very low